Welcome to the deep dive. Today we're plugging into something really fundamental, electrical fundamentals in aviation maintenance.
That's right. We've got some great material here pulled straight from EASA Module 03.
Marshall's O3. So that's the foundational stuff for maintenance techs, right? Covering the basics for A1, B1, B2, B3 licenses.
Exactly. And what's pretty amazing is just how much ground these excerpts cover. We're talking everything from, the very nature of electricity itself,
Reach down into the atoms.
right down to atoms, electrons, and then scaling all the way up to complex AC/DC circuits, motors, generators, basically the stuff that makes aircraft go, electrically speaking.
Okay, so our mission for this deep dive then is to really get into the core of it, not just skim the surface.
Yeah, pull out the key principles, maybe some surprising insights that you might miss just reading a textbook.
And make these sometimes pretty complex ideas feel understandable and relevant.
Hopefully by the end, you'll have a much clearer view of that essential electrical foundation, the bedrock for all the fancy electronics in modern planes.
Sounds good. So where do we even begin with something this big?
Well, you have to start small, right? With the absolute building blocks. Electrons and atoms.
Electrons and atoms. Okay, seems simple enough, but I bet there's a catch. What's this fundamental uncertainty about electrons the source mentions?
It's fascinating, really. Even at this basic level, there's this question. Is an electron just a negative charge without any real mass? Or is it an actual particle, like a tiny bit of matter, that carries a negative charge?
Huh. So we don't actually know for sure?
Well, the material points out that for calculating atomic weight, the electron's mass is considered negligible, basically zero. But the fundamental nature, still a bit of a mystery we build on.
That's actually kind of mind-blowing, basing all this complex tech on a fundamental question mark. Okay, let's look at atoms. Hydrogen is the simplest.
Yep, one proton in the nucleus, one electron orbiting. That's it.
And then you compare that to something like oxygen.
Big difference. Oxygen's got 8 protons, 8 neutrons in the nucleus, and then 8 electrons whizzing around in 2 different shells or energy levels.
So the complexity ramps up quickly. What keeps an atom sort of electrically balanced? What makes it neutral?
Simple balance. Equal number of positive protons in the nucleus and negative electrons orbiting. The charges cancel out. Neutral atom.
And how does it become an ion? Cation anion. I always mix those up.
Easy way to remember. If an atom loses electrons, it has more protons left, so it becomes positively charged. That's a cation. Think cat positive.
Huh, okay, I'll try to remember that. And anions.
If it gains extra electrons, it gets more negative charge than positive. That's a negative ion, an anion.
Lose electrons, positive canyons. Gain electrons, negative anion.
Got it.
Now, what about valence electrons? Why are they singled out?
They're the important ones for chemistry. They're the electrons in the outermost shell of the atom.
The ones on the edge.
Exactly. They're the ones that get involved in forming bonds with other atoms. They determine the atom's valence, basically how it connects with others. They're the social butterflies of the atom world.
Okay, the sociable electrons. That leads nicely into conductors and insulators. What's the key atomic difference?
It really boils down to free electrons. How many electrons are loosely bound and can easily move around within the material?
So conductors.
Conductors like silver, copper, they're packed with these free electrons, current flows easily.
And insulators.
Insulators, glass, ceramic, plastic have very few free electrons willing to move. They resist current flow strongly.
And semiconductors were mentioned too.
Yeah, they're in the middle. They have some free electrons, but not as many as conductors, and their conductivity can be changed under certain conditions. We'll probably get more into those later.
Okay, so free electrons are the key. Let's shift gears. Static electricity. The zap you get touching a doorknob. What's happening there?
Fundamentally, it's just an imbalance of charge. Too many electrons or too few on a surface or within a material.
And the basic rule.
Like charges repel, push each other away. Unlike charges attract, pull together. Positive repels positive, negative repels negative, but positive and negative attract. Simple as that.
Makes sense. How do we measure this charge imbalance? There's a unit, right?
Yes, the coulomb, capital C. And the number of electrons in 1 coulomb is just staggering.
How staggering are we talking?
About 6.241 times 10 to the power of 18 electrons. That's 6.241 billion electrons, roughly.
Wow. Okay, that puts a little static shock into perspective. How do things get charged up in the first place? Friction.
Friction is a big one. Rub 2 different materials together, electrons can jump from one to the other. One becomes positive, the other negative.
And contact. The source mentioned touching a charged rod to a metal bar.
Right. If you bring a positively charged object near or touching a neutral conductor, like that metal bar, the free electrons in the bar are attracted towards the positive charge.
So they move towards the contact point.
Exactly. They shuffle over, leaving the rest of the bar with a net positive charge because it's now short on electrons. The charge gets shared in a way.
Okay, now, in aviation maintenance, this isn't just about annoying shocks. ESD, electrostatic discharge, is a serious problem.
Oh, absolutely huge. ESD is a major cause of damage to sensitive electronic components. Think circuit cards, LRUs line replaceable units.
So just touching a connector pin could fry something expensive.
Easily. Even the static buildup on a technician or sliding something across a carpeted workbench, it can all lead to damage that might not even show up immediately. Costly stuff.
Ouch. So what are the non-negotiables for preventing ESD damage?
Grounding is paramount. Always discharge yourself by touching a grounded part of the equipment before touching any components.
Like a chassis.
Yeah, the metal frame usually works. And definitely use grounding wrist straps. They provide a continuous, safe path for any static buildup to dissipate.
And just generally handle components carefully.
Right. Use protective caps on connectors. Keep sensitive parts in their special anti-static bags or containers until you're ready to install them. Respect the sensitivity.
Grounding and careful handling. Got it. Let's move to charge and motion current. But first, we need the push, right?
Yeah.
Voltage.
Exactly. Voltage, or potential difference, is the electrical pressure. The source uses that great water tank analogy.
Yeah, the two tanks, different water levels.
Right. The pressure difference makes water flow from high to low. Voltage is like that pressure difference for electrons. It's the difference in electrical potential energy between 2 points that motivates charge to move.
And there's a formula, E equals W over Q, energy per unit charge.
Correct. Potential difference E is the energy, W in joules, needed to move a unit of charge, Q in coulombs, between 2 points. It defines how much push you get per charge.
Okay, voltage is the push. Now, define current for me again, the actual flow.
Current, symbol I, is the rate of flow of charge. How much charge passes a point per second. The formula is I equal Q.
Q is charge in coulombs, it is time in seconds.
Yep. And the unit is the ampere, or amp A. 1 amp is 1 coulomb of charge flowing past a point every second.
Which, going back to that huge number, means 1 amp is roughly 6.24 billion electrons flowing past every single second.
Mind-boggling numbers, really.
Now, DC versus AC. We'll get deeper into AC later, but what's the simple definition of DC? Direct current.
Dead simple. The charge flows consistently in one direction, like from a battery. Negative terminal through the circuit back to the positive, polarity stays constant.
Okay. Now this drift velocity concept, electrons move slowly, but the effect is fast. The steel ball analogy.
Yeah, this trips people up sometimes. Individual electrons in a wire don't actually race along at the speed of light. They bump around, drift relatively slowly. That's the drift velocity.
So why does the light turn on instantly?
Think of that tube full of steel balls. Push one in at one end, one pops out the other end almost immediately, right?
Yeah, the push travels through the line of balls instantly.
Exactly. The effect of the voltage, the electrical field push, propagates through the wire nearly instantaneously, making all the free electrons start drifting almost at once. It's the chain reaction that's fast, not the individual electron's journey. Ah, okay. The signal travels fast, the messengers are slower. Clever analogy. Where does this electrical energy actually originate? The source listed a few methods. Pressure, chemical reactions, heat, thermal energy, and light were the main ones mentioned.
Pressure, like squeezing a crystal. Piezoelectricity.
Precisely. Some materials generate a voltage when you physically stress them, used in sensors, lighters, that sort of thing.
And chemical sources. Batteries, obviously. The lead-acid battery got some detail.
Yeah, the classic. Positive and negative plates, lead and lead oxide swimming in sulfuric acid electrolyte, separators to stop shorts, all in a case with vents.
Vents because explosive gases.
Hydrogen and oxygen can be produced during charging, especially overcharging. That mixture is definitely explosive, so proper venting is critical. Aircraft often have special drain systems to neutralize acidic fumes, too. Safety first.
Always. How do we combine batteries to get different results? Series versus parallel.
Connect them in series, positive to negative, and the voltages add up. More push.
Okay. And parallel.
Connect them in parallel, all positives together, all negatives together. The voltage stays the same, but you increase the total amp-hour capacity. More endurance, basically. It can supply the current for longer.
Series for volts, parallel for capacity. Makes sense. What affects how long a battery lasts? The charge-discharge cycles?
Several things. Over-discharging is bad, can cause sulfation, where hard crystals form on the plates and reduce capacity.
Don't run them completely flat.
Ideally, no. Also, charging or discharging too fast generates heat and can damage the plates. Temperature extremes, hot or cold, aren't great either. Gentle use is best for longevity.
Right. Testing lead-acid batteries, specific gravity readings.
Yeah, using a hydrometer to measure the density of the electrolyte, it tells you the state of charge. But, and this is important, measure it before adding any distilled water.
Why before?
Because the water needs time to fix properly, otherwise you get a false low reading. And handle that electrolyte with extreme care. Sulfuric acid burns are nasty.
Understood. Safety gear mandatory.
Yeah.
What about NiCad batteries? Different chemistry, different issues.
Nickel cadmium. They also produce hydrogen and oxygen during overcharging, so they need relief valves and good ventilation too. Big difference in applications sometimes.
How so?
NiCads are often better for applications needing lots of deep discharge cycles, high current demands. Sealed lead acid, SLA batteries, are often preferred for standby power, like emergency lighting, where they sit charged for long periods.
Different tools for different jobs. Okay, last energy source mentioned. Thermocouples.
Right. This uses the thermoelectric effect. Join two different metals, heat the junction, and you get a small voltage. Tiny, really millivolts.
It's all for powering things.
No, but perfect for temperature measurement. The voltage produced is directly related to the temperature at the junction. That's how we measure cylinder head temp, CHT, or exhaust gas temp, EGT, in engines.
So they're high temp sensors. Okay, we have voltage, push, current flow. Now the opposition, resistance.
Resistance, symbol R, it's the property of a material that opposes the flow of current, measured in ohms using the Greek letter omega.
And it dictates how much current flows for a given voltage.
Exactly. 1 ohm of resistance will allow 1 ampere of current to flow when 1 volt of potential difference is applied across it. It's the electrical friction.
Which brings us straight to the cornerstone, Ohm's law.
Absolutely fundamental. E equals IR. Voltage E equals current I times resistance
If
R.
I can rearrange that, right? I is ER. R to I.
Yep, the famous Ohm's law triangle or wheel helps visualize those relationships. Super useful for calculating any one value if you know the other two. Essential for troubleshooting.
Definitely. How does this work with resistors in series, one after another? The source mentioned voltage drops.
In a series circuit, there's only one path for the current, so the same current flows through every resistor.
Okay.
But each resistor uses up some of the voltage supplied by the source, that's the voltage drop across that resistor, and VIR still applies to each one individually.
So the voltage gets divided.
Precisely. The total voltage supplied by the source is equal to the sum of all the individual voltage drops across each resistor in the series loop. That's Kirchhoff's voltage law. Larger resistances get a larger share of the voltage drop.
Which leads to voltage dividers, making lower voltages from a higher one.
Exactly. A very common circuit. Just use 2 or more resistors in series. You can tap off a specific lower voltage across one of the resistors. The source even showed how changing your ground reference point can give you positive or negative readings relative to that ground. Clever stuff.
Very useful. What about parallel circuits? Multiple paths for current. The source called them current dividers.
Right. In parallel, the voltage across each branch is the same. It's the source voltage.
But the current splits.
Yes. The total current from the source splits up, flowing through the different parallel paths. More current goes through the path with less resistance. It's inversely proportional.
Makes sense. The easier path gets more flow.
And that's where Kirchhoff's current law comes in. The total current flowing into any junction or point in the circuit must equal the total current flowing out of that junction. Conservation of charge. Nothing gets lost.
Into equals out. Simple but powerful. We've covered series, parallel. But about combination circuits? Series, parallel.
Just means you have elements of both in the same circuit. Some parts in series, some in parallel.
Sounds complicated to analyze.
You just break it down. Find the equivalent resistance of the parallel sections first. Then treat that equivalent resistance as a single resistor in series with the other parts, or vice versa. Apply Ohm's and Kirchhoff's laws step by step. It's like a puzzle.
Okay, piece by piece. Let's dig into resistance itself more. What makes a material more or less resistive?
4 main factors. First, the material itself, how many free electrons it has. Copper, good, rubber, bad, for conduction anyway.
Second.
Length, longer wire, more resistance. Directly proportional.
Third.
Cross-sectional area. Thicker wire, less resistance, more room for electrons to flow.
Sure.
Inversely proportional.
And fourth, temperature.
Usually, yes. For most conductors, resistance increases as temperature goes up. Atoms vibrate more, get in the way of electron flow.
And that temperature coefficient of resistance thing.
That just quantifies how much the resistance changes per degree change in temperature for a specific material. Positive for most metals, can be negative for some materials like semiconductors.
Interesting. Now, wires. AWG, American Wire Gauge.
Standard system for wire diameter, mostly in North America. Key thing, it's inverse. Lower AWG number means a thicker wire.
So lower number, thicker wire, less resistance.
Exactly, and there's a rule of thumb. Go down 3 gauge numbers, you roughly double the area and have the resistance. Go up 3, you have the area, double the resistance.
Candy shortcut. What about flat conductors? Bus bars.
Same principles. Resistance depends on material, length, cross-sectional area. For a rectangular bar, area is just thickness times width, still measured in ohms.
Okay. Now, actual resistor components. Carbon film, metal film, wire wound.
Yeah. They're all designed to provide a specific resistance, but they differ in how they're made and what they're made of. This affects their precision, stability, power handling, and cost.
So different applications need different characteristics.
Right. Carbon film might be cheap and common, metal film more precise, wire wound good for handling higher power. You choose based on the circuit's needs.
And they aren't perfectly accurate. Tolerance.
Correct. Tolerance is the allowed percentage difference between the marked value and the actual resistance. 5%, 1%, even less for precision circuits, usually shown by a color band.
The color code. We won't decode it now, but it tells you the value and tolerance. What about variable resistors? Rheostats and potentiometers.
Both let you adjust resistance. A rheostat typically controls current. It's usually used with 2 terminals.
And a potentiometer.
Usually used to divide voltage. It has 3 terminals, 2 ends, and a movable wiper in the middle. Think volume knob. By moving the wiper, you pick off a variable voltage.
Rheostat for current, potentiometer for voltage. Got it. Let's talk power, work, and energy. Related, but different concepts.
Definitely. Power P is the rate of doing work or using energy. How fast energy is transferred. Unit is the watt W, which is 1 joule per second.
And P equals W work or energy over time.
Yep. And in electrical terms, we have those handy formulas derived from Ohm's law.
PEI?
Power equals voltage times current. Also, PERIR, current squared times resistance, and PERER, voltage squared divided by resistance. The power wheel shows all these.
Very useful for calculations. What about energy itself?
Energy is the capacity to do work. Since power is the rate of energy use, energy equal power, S time.
Unit is the joule, or watt second.
Yes, the base SI unit is the joule, J, which is 1 watt second. But for practical electricity usage, we often use the kilowatt hour, kWh. That's what your electricity bill measures. Yeah. 1 kilowatt of power used for 1 hour.
Right, the meter spinner. Okay, let's add another component, the capacitor. Stores charge differently than a battery?
Yes. Capacitance C is the ability to store charge in an electric field. A capacitor is basically 2 conductive plates separated by an insulator, the dielectric. Apply voltage, charge builds up on the plates.
Measured in farads.
F, correct. And a key behavior, a capacitor blocks steady DC once it's charged.
But it passes AC.
Yeah.
Or the effects of changing DC.
Exactly. Because the voltage is changing, the capacitor is constantly charging and discharging, allowing current to flow in the circuit connected to it, even though nothing crosses the dielectric.
So it acts like a filter in some ways.
Mm-hmm.
How does it charge and discharge in DC, this time constant idea?
When connected to DC via a resistor, it charges exponentially. Disconnect the source, provide a path, it discharges exponentially. The time constant, tau, tells you how fast.
R times C.
Resistance times capacitance. In one time constant, it charges to about 63% of the final voltage, or discharges down to about 37% of its starting voltage. After about 5 time constants, it's considered fully charged or discharged for practical purposes.
So RC determines the charge-discharge speed. How do capacitors combine? Parallel versus series.
Parallel is easy. Total capacitance is just the sum. C total plus C OFLA plus barnacle plate area.
In series, it's the weird one, right?
Right, it's like resistors in parallel. The reciprocals add up. 1 C total equals 1 C ORO plus E OR. Total capacitance is less than the smallest individual one, like increasing the dielectric thickness.
Opposite of resistors. Okay. Now, AC circuits. How do capacitors behave there?
With AC, the voltage is constantly reversing, so the capacitor is constantly charging and discharging back and forth. Current flows continuously in the external circuit.
And the current leads the voltage. What does that mean?
It means the current reaches its peak value in the cycle before the voltage across the capacitor reaches its peak. By 90 degrees in a purely capacitive circuit.
Why?
Because current has to flow first to build up the charge, and thus the voltage, on the plates. Charge flow current happens before the potential difference. Voltage is fully established.
Okay, that makes sense. And this opposition to AC current is capacitive reactance.
Yes, XC. Measured in ohms, just like resistance. But it depends on frequency.
How so? Formula.
XC equals 1 to FFC. It's inversely proportional to both frequency F and capacitance, C.
So higher frequency means lower reactance, less opposition.
Exactly. Capacitors let high frequencies pass more easily than low frequencies.
Consistent with blocking DC, zero frequency. What about different types? Paper, polyester, oil?
Different dielectric materials. Affects voltage rating, capacitance range, stability, cost. Polyester film is common. Oil-filled, often used for high-voltage applications due to better insulation. Depends on the job.
Got it. Let's switch to magnetism, another fundamental force tightly linked to electricity. Basic principles.
Source starts with visualizing fields using iron filings. They line up along magnetic flux lines. These lines conventionally go from North Pole to South Pole externally, forming closed loops.
Permanent magnets versus soft iron.
Permanent magnets hold their magnetism, high retentivity. Soft iron magnetizes easily in a field, but loses most of it when the field is removed, though it keeps a little bit residual magnetism, which is important later for generators.
Horseshoe magnets, just a bent bar magnet.
Pretty much. Bending it brings the poles closer, concentrates the field in the gap between them. Stronger, more uniform field there.
And magnets need care. Don't drop them.
Yeah. Shock, extreme heat, strong opposing fields can weaken them. Keep neodymium magnets dry, store magnets with opposite poles together, or use keepers, soft iron bars across the poles, to maintain the magnetic circuit.
Good tips. Now the link. Electromagnetism. Current creating magnetism.
The core idea. Current flowing in a wire creates a magnetic field around it. The left-hand rule helps visualize the direction.
Thumb points in current direction, fingers curl in field direction.
That's the one for a straight wire.
What if you loop the wire? Or make a coil?
Looping concentrates the field inside. Coiling it many times, a solenoid, makes a field much stronger, acting like a bar magnet with north and south poles. More turns, stronger field for the same current.
And putting an iron core inside.
Dramatically increases the strength. The iron core becomes strongly magnetized by the coil's field, and its own field adds to the coil's field, magnetic amplification.
Used everywhere, I imagine. Relays.
Classic example. Current in a coil magnetizes a core, which pulls in an armature to physically open or close switch contacts. A small current controls a larger one. Also motors, generators, instruments.
Okay. Related concept. Inductance. Property of a coil.
Inductance L, measured in Henry's H. It's the property of a coil to oppose changes in the current flowing through it.
How does it oppose the change?
When current changes, the magnetic field changes. This changing field induces a voltage, back EMF, in the coil itself that fights the original change, tries to keep the current steady, like electrical inertia.
Where does the energy go when it resists this change?
It's stored in the magnetic field built up in the inductor's core. The core material, air, ferrite, iron, toroid, affects the inductance value and how much energy it can store.
And like capacitors have capacitive reactance, inductors have inductive reactance.
Exactly. XL, also measured in ohms, opposition to AC current flow.
Formula. How does it depend on frequency?
XL equals 2FL. It's directly proportional to both frequency F and inductance L.
So higher frequency means higher reactance, more opposition.
Correct. Inductors block high frequencies more effectively than low frequencies, opposite of capacitors.
Interesting symmetry there. How do inductors combine in circuits?
Just like resistors, in series they add up L total L arrow plus L plus L.
Are they parallel?
The reciprocals add 1L total Leon plus 1L or plus 1L L few. Same rules for combining their reactances XL in AC circuits.
Okay, behaves like resistance for combinations. Now, the big applications.
Yeah.
Generators and motors. Converting energy. Generators first. How do they make electricity?
Electromagnetic induction. Move a conductor through a magnetic field so it cuts the flux lines, or move the field past the conductor. Either way, you induce a voltage in the conductor.
And the voltage depends on?
Speed of cutting the lines and strength of the magnetic field. Faster motion or stronger field means more voltage. Connect the conductor to a circuit, current flows. Mechanical energy to electrical energy.
DC generators versus alternators. AC generators.
DC generators produce direct current, one direction. Alternators produce alternating current, reverses direction, both used in aircraft, often for 14V or 28V DC systems, but AC has advantages we'll get to.
How does a DC generator get that one-way output, the commutator?
Right. The rotating coil armature actually generates AC internally as it spins in the field. The commutator is a segmented copper ring rotating with the armature. Stationary brushes ride on it.
And it switches connections.
Exactly. It mechanically reverses the connection between the internal coil and the external circuit, just as the internal voltage reverses. So the output seen by the brushes is pulsating DC, always flowing the same way. Clever mechanical rectifier.
Very clever. What types of DC generators are there?
Depends on how the field windings, making the magnetic field, are connected. Series wound, field in series with armature. Shunt wound, field in parallel with armature. Or compound wound, both series and shunt fields. Each has different voltage current characteristics under load.
And separately excited.
Means the field gets its power from a separate source, often controlled by a voltage regulator for stable output.
Maintenance on these brushes and commutators seem key.
Absolutely. Keep them clean, check brush wear and spring tension, inspect commutator surface for pitting or burning. Secure mounting, clean connections are also vital. And never use emery paper on the commutator conductive particles. Fine sandpaper only, if needed.
Good safety tip. Now, motors. Opposite function, electrical to mechanical energy.
Exactly. Based on the force on a current-carrying wire in a magnetic field. Remember the parallel wires? Same direction current attracts, opposite direction repels.
So that force makes things spin.
In a motor, you put a current-carrying coil, armature, in a magnetic field. Forces on opposite sides of the coil create torque, making it rotate.
And the commutator again?
Yes, in a DC motor, the commutator reverses the current direction in the coil at the right moments to keep the torque pushing in the same rotational direction. Continuous spinning.
Basic parts are similar. Field frame, armature, commutator, brushes.
Yep. Field frame holds the magnet's field windings. Armature is the rotating coil assembly with commutator. Brushes make contact. End frame holds bearings.
And types are similar too. Series, shunt, compound.
Yes, based on field armature connections. Series gives high starting torque but variable speed. Shunt gives more constant speed. Compound is a mix. Different jobs need different characteristics.
What's this counter EMF or back EMF in motors?
Crucial concept. As the motor's armature spins, it's also acting like a generator, inducing its own voltage.
But it opposes the applied voltage.
Exactly. This back EMF pushes against the supply voltage, reducing the net voltage across the armature. This naturally limits the current the motor draws. The faster it spins, the higher the back EMF, the lower the current for a given load. It's self-regulating.
Without it, the motor would draw way too much current.
Oh yeah, armature resistance is usually very low. Back EMF is essential for normal operation.
How do you reverse a DC motor?
Two main ways. Split field motor uses two opposite field windings, energize one or the other. Or use a switch, like a DPD2, to reverse the current direction in either the armature or the field windings, but not both. That reverses the torque.
Flip the field or flip the armature current. Makes sense. Speed control.
Usually by varying field strengths or armature voltage. Use a rheostat in the field circuit. Weakening field speeds up shunt motors. Or in series with the armature, reducing armature voltage slows it down.
So variable resistors are key there too. Maintenance tips for motors. Similar to generators.
Pretty much. Cleanliness, tight mounting, check brushes and commutator, inspect wiring, lubricate only if specified. And remember to check the load and external circuit if a motor seems faulty.
Good point. Now, AC. Why is it often preferred over DC, especially in aircraft?
Several big reasons. AC is easily transformed up to high voltage for efficient transmission. Less current means less IR loss, then step down. AC motors are often smaller, lighter, simpler than DC motors for the same power.
And no brushes in many AC motors.
Big advantage, especially at high altitude where DC commutation can be tricky. AC circuit breakers also tend to work better at altitude. Plus, even DC aircraft often need some 400 Hz AC for specific equipment.
Frequency F depends on the number of magnetic poles, P on the rotor and the rotor speed, RPM. Formula is F, P2, RPM 60. More poles or faster spin means higher frequency. 400 Hz allows for smaller, lighter components compared to 50, 60 Hz ground power.
Okay. AC waveforms. In phase versus out of phase. In phase means two waveforms, like voltage and current, peak and cross zero at the exact same times. Perfectly synced. Out of phase means they're shifted relative to each other.
Measured in degrees. Leading or lagging.
Yep. If one peaks before the other, it's leading. The other is lagging. The difference is the phase angle. 180 degrees out of phase means they are exact opposites.
Timing matters. How do we measure AC voltage current effectively? RMS value.
RMS means root mean square. It's the effective value of AC. It's the equivalent DC value that would produce the same amount of heat in a resistor.
So let's just compare AC and DC power capability.
Exactly. For a sine wave, VRMs is about 0.707 times the peak voltage. Unless stated otherwise, AC values are usually RMS. Meters measure RMS.
Got it. What about non-sinusoidal waves, square or triangular?
Found in electronic circuits, digital stuff, control signals, oscillators. Not typically the main power distribution waveform, which is sinusoidal, but definitely used within systems.
Yeah. Now, total opposition in AC circuits. Resistance plus reactance equals.
Impedance. Symbol Z. Also measured in ohms. It includes both resistance R and the net reactance, X, which is XL minus XC, or vice versa.
And they combine like vectors. Pythagorean theorem.
For simple series circuits, yes. ZVA circle equals R plus X denaris. Impedance is the overall opposition considering magnitude and phase effects.
Okay, Z is the total AC opposition. Power in AC circuits. Not just V times I.
Not if there's reactance because voltage and current are out of phase. V times I gives apparent power, VA.
But the power actually doing work is?
True power, watts, calculated as P, true equals Z, I cos, where I is the phase angle. Cos is the power factor, tells you how much of the apparent power is actually doing work.
And the rest is?
Reactive power, VR. Power sloshing back and forth due to capacitors and inductors storing and releasing energy. Only resistance consumes true power.
Apparent, true, reactive power. Need to know the difference. Let's talk transformers. Essential for AC. How do they work?
Pure electromagnetic induction. AC in the primary coil creates a changing magnetic field in the iron core. This changing field induces an AC voltage in the secondary coil. No direct electrical connection.
And voltage changes based on the turns ratio.
Exactly. VPVs, aviary NPNs. Primary voltage over secondary voltage equals primary turns over secondary turns. More turns on secondary, voltage steps up. Fewer turns, steps down.
Crucial for power grids and electronics. Are they perfect? Any losses?
No, always some losses. Copper losses, IOR heat in the windings due to their resistance, and core losses.
Core losses.
Two types. Hysteresis loss, energy loss reorienting magnetic domains in the core, and eddy current loss, circulating currents induced within the core material itself, causing heat.
How do they reduce eddy currents?
By making the core from thin, insulated sheets called laminations. This breaks up the paths for large eddy currents.
Smart design. Now, using capacitors and inductors as filters, based on their frequency response.
Precisely. Capacitors pass high frequencies easily, low XC, block low frequencies, high XC. Inductors do the opposite pass, low XL, block high XL.
So you can use them to smooth DC from a rectifier.
Yeah. A capacitor in parallel shunts the AC ripple to ground. An inductor in series blocks the ripple from getting to the load. Both help smooth the pulsating DC.
Combining them gives LC filters, L, T, pi configurations.
Right. Combining L and C gives sharper, more selective filters. The configuration, L, inverted L, T, pi, determines the specific frequency response.
And the basic types are low pass, high pass.
Low pass lets low frequencies through, blocks high. High pass does the opposite. Band pass lets a specific band through. Band stop, or notch, blocks a specific band. These are passive filters, no external power needed.
A whole toolkit for shaping signals. Back to alternators. Why the rotating field design in aircraft? Stationary armature.
Primarily safety and reliability at high voltage. The high power output comes from the stationary armature windings. No need for high voltage slip rings or brushes, which can arc at altitude.
So the low power field current goes through the slip rings.
Exactly. Much easier and safer to handle lower voltage current on the rotating part. Allows for better insulation and construction of the stationary high voltage windings too.
Makes sense. Alternator ratings, what we need to know.
Key specs are apparent power, kVA, voltage, frequency, usually 400 Hertz, number of phases, often three-phase, and power factor. Three-phase gives three voltages 120 degrees apart.
How are they tested? Load banks.
Yes. Load banks provide a controllable electrical load, resistive, inductive, etc., to simulate aircraft demands. Lets you test the alternator's output and stability under various conditions.
Essential for verification. How is the voltage kept constant? Voltage regulation.
Basic idea is to control the field current. Simple way is a rheostat in the field circuit. More sophisticated is an automatic voltage regulator.
The vibrating contact type?
Yeah, senses output voltage. If low, contacts close, bypass resistance, increase field current, boost voltage. If high, contacts open, insert resistance, decrease field current, lower voltage. Vibrates rapidly to maintain an average voltage.
Clever electromechanical feedback. What about reverse current sensing? Protection.
If an alternator fails and its voltage drops below the bus voltage, it can start drawing power from the system. Reversed current protection detects this and automatically disconnects the faulty alternator, prevents it draining the system. Critical safety feature.
Absolutely. Now, constant speed drives, CSDs, needed because engine speed varies, but alternator needs constant speed for 400 hertz.
Exactly. The CSD is a transmission between the engine gearbox and the alternator. It takes variable input speed from the engine and delivers constant output speed to the alternator, ensuring stable 400 Hz output, usually a hydromechanical device.
Ingenious piece of kit. What about AC motor generator sets and inverters?
Motor generator sets are usually for ground power or use ground AC to drive a motor connected to an aircraft-type alternator for testing. Inverters convert DC to AC. Older rotary types use spinning parts. Modern static inverters use solid-state electronics to chop up DC and synthesize AC. More efficient and reliable.
Different ways to get AC when you need it. Finally, AC motors. Simpler than DC.
Generally, yes. Lighter, smaller for the same power, and induction motors, most common type, don't need brushes or commutators. Less maintenance, better at altitude.
Speed depends on frequency and pulse.
Yep. Speed, RPM, equals 120 frequency pulse. With 400 Hz, they can run very fast, often needing gear reduction for the driven equipment.
What about synchronous motors?
They run at a speed locked exactly to the AC frequency, no slip, but they aren't self-starting, need help getting up to speed, then they lock in. Used where precise speed is critical.
Fascinating precision. Well, that covers a huge amount of ground.
It really does. From electrons to complex machines, all based on these fundamental principles from EASA Module 03.
Absolutely. And you can see how understanding this stuff is just non-negotiable for aviation maintenance. It underpins everything electrical on the aircraft.
No doubt. And when you think about modern aircraft, all the digital avionics, complex power management, it all still relies on these core electrical and magnetic concepts.
It really makes you think, doesn't it? How these fundamentals scale up to control such incredibly complex systems. Maybe that's a topic for another deep dive. How these basics enable things like fly-by-wire or integrated modular avionics.
That sounds like a great direction to explore next time. There's always more to learn.
There certainly is. Well, thank you for guiding us through this electrifying journey today. Really appreciate the insights. Until our next deep dive, everyone.